Welcome to all you beginning statisticians learning about normal distributions. And in this particular video, we're going to talk about using the calculator to find the area under the curve or the probability of a particular value being higher or lower or between some other values. Okay, so in other words, we've done this before, but not with the graphing calculator. We used a table. And with the table, we use Z-scores. So in other words, we don't need any Z-scores because we're not going to use the table. And the table is for Z-scores. And the table I'm referring to is this one. So when we use this one, we're using Z-scores. So let's look at an example, a pretty simple example, and compare what it looks like with Z-scores to what we can do with the calculator. So let's say that I have, let's call this example 1. I have a certain set of data that is normally distributed. I need to know that it's normally distributed, and it has a mean of 50 and a standard deviation of 6. And I'm being asked this. Now, what does that mean? That means what is the probability that if I just randomly chose a point that I know is in my normal distribution, what is the probability that that data point would be less than 52? Now remember, the table is strictly about less than values. The entire table is telling you, for whatever X value you find the Z-score of, the probability of being to the left of that. Less than is to the left of on these, and greater than would be to the right. So if we want to know the probability of being less than 52, let's look at what this would look like. I'm going to go ahead and fill in those numbers, the standard deviation markers, so to speak. In other words, 50 is the mean, and one standard deviation above that would be at 56 because I add 6 from right here, and 2 would be at 62, and 3 would be at 68, and then subtract 6 to go to the left. Okay, so I like to always go ahead and do this. This chart with the percentages of like 34%, 13.5%, remember that's called the empirical rule. So I like to go ahead and fill this out so that I know for sure whether the data mark that I'm being asked about, whether that point or that location is exactly 1 standard deviation or 2 standard deviations or 3 standard deviations above or below the mean. And it clearly is not because I don't see 52 here. So that's when now we have used Z-scores. So that's maybe here. And so the way Z-scores work are, you have your value, you want to know what the probability of being less than that is. So we're looking for the probability that if I randomly pick a piece of data somewhere under this curve, the probability that's in the orange shaded region. Okay? So with this, you have a couple of steps. First, you have to convert that to a Z-score. Then you go to the table and you look for that Z-score. And that will tell you the probability of being less than that particular value. So to convert it to a Z-score, remember our formula is I take, whoa, we're at the wrong thing first. My data point, or my X, minus the mean, all divided by the standard deviation. So here that's 52 minus 50 divided by 6, so that's 2 divided by 6, or about 0.3. And I'm going to the 10th place just because my table goes to the 10th place. So that is the Z-score. That number right there, that is my Z-score for 52. And then I go to this chart, and I find my Z-score for 52 is 0.3, so I'm going to look at 0.3. Now, it's 0.3. It's positive. So I have to go to the one that says positive 0. So positive 0, 0.3 is right there. So 0.6179. So that is the probability that if I randomly choose a piece of data in my distribution, that it will be less than 52, is 0.6179. Probably should be approximate because the table is giving me approximate values. But now as a percentage, that would be 61.79%. So 61%, another way of thinking of that is 61.79% of my data is to the left of 52, is less than 52. Now, if I had been asked, what is the probability of your randomly chosen point being greater than 52? The table only gives me less than. But altogether, the probability it's either less than or greater than, it has to be one or the other. So that's a probability of 1. So if I wanted to know the probability that X was greater than 52, I would do 1 minus, I'd still have to go find that same number on the Z-score chart on the table, and then I would subtract that number from 1. And let me just make sure, I think it's 0.3821. Let me make sure that I got that right. I did one wrong in a Zoom session earlier today, so there we go. 0.3821. Makes me trust myself less. So in other words, that's about a 38.21% chance. And really, I should have written approximately over here. Most teachers, though, are not going to get upset with you if you don't do the approximately equal to. All right, so that's using the Z-scores. So again, we do it when we are looking for numbers that are not 1 standard deviation, 2 standard deviations, 3 standard deviations above or below the mean. And we do it when we're not using the calculator. Okay, so we take our data point, we find the Z-score using the formula, then we take it to the table. The table tells us the value to the less than, so if I need to know to the right of, greater than, or in between two numbers, then I have to play with that a little bit. But before we do one where we're doing in between two numbers, let's do this exact same problem with the calculator. Okay, now, okay, so when we do this one with the calculator instead, there are 4 things we need to know. Okay, and those 4 things are a lower boundary, which is basically the left side of the area we want to find, an upper boundary, which is basically the right side. We need mu and we need sigma. Okay, so in other words, here we just had one number we needed to worry about. We didn't need a left and a right. So when we need a left and a right, what that looks like is this. If we want to know this area, then the left is like over here, and here's the right. So 52 would be my right boundary or upper boundary because it's higher. And we basically just have to pick a really low number compared to the rest of the data to be our lower boundary. What I usually do is just put in a bunch of 9s. And if it's negative, that'd be like 999, something like that. Okay, and you could put in another 9. You could put negative 9,999. But just put in something very small compared to the rest of the data to show, it's almost like you're trying to give a numerical quantity, a numerical identification to negative infinity, because that's kind of what's going on. So as long as you make it much smaller than anything here, you should be good. So for this, my 4 numbers I need, here's my lower boundary. Here is my upper boundary. And there's mu and sigma. Okay, so when I go to the calculator, and the 83 and the 84 work slightly differently, if I press, basically, remember this is a normal distribution. So I'm going to go to distr, D-I-S-T-R stands for distribution. Okay, so it's right above vars, right where my finger is. So I'm going to do second vars to go to distributions. And the second one down is the one we will use, normal CDF. So I'm going to press the number 2, and it says normal CDF, and then it gives me an open parentheses. Now, your graphing calculator might instead specifically have a list and ask you to fill these things in. Mine is really kind of the harder way, is that you have to know what the order is they want you to fill in. And this is what it wants. Okay, so I'm going to use commas to separate these 4 values. Okay, we talked about what those 4 values were for this particular problem. The lower boundary, or the far left, I'm just going to put like negative 999. The upper is 52, mu is 50, and sigma is 6. Remember, mu is the mean, sigma is the standard deviation. So lower, it's important to have that negative there because it has to be on the far left. Upper is 52, comma. The comma is right above 7. Mu is 50, comma, and sigma is 6, close my parentheses, and it gives me the same thing the table gave me. It gives me the percentage of the data to the left. Actually, it doesn't. It just gives me exactly what I'm asking for. I apologize. But this is, in this particular case, this is the percentage of the data to the left of that. So now when we did it with the table, we got this. When we do it with the calculator, we're going to get something slightly different. We got this. Okay? And it's okay because they're pretty close. This is like 62% and this is like 63%. So it's still very, very close. Sometimes it's even closer than that. But that's how I do it with the calculator. Get the exact same thing as the table. All right, so let's do some more like that. I have some more problems pulled up on my computer I want to show you. Okay, this first one here says the mean life of a properly inflated tire is 30,000 miles. The standard deviation is 2,000 miles. What would you enter into the calculator, and what percentage of the life of the tires would be less than 29,000 miles? Okay, so for that particular problem, again, it said the mean life of a properly inflated tire is 30,000 miles. So the mean is 30,000. The standard deviation is 2,000. Okay, so 32,000, 34,000, and so on. And on this side, we have 28,000, 26,000, and 24,000. Okay, so now they are asking me what percentage of the life of tires, and I guess if we're talking about a whole bunch of tires that have died, what percentage of them would have a life less than 29,000 miles. So 29,000 is about right here. Less than is this way. So we're talking about everything to the left of there. All right. Now, this is the upper boundary of the region we're looking at because we're going to the left from that. The upper boundary is always like the right-hand side of your region. So the lower boundary, way over here, almost like negative infinity. Let's just call it -9. Let's do a bunch of 9s. There we go, because we're in the thousands here. Okay, just make it a very big negative number or a very small number. Okay, that's the left side. The left side is your lower boundary. Mu is 30,000 here. And sigma is 2,000 here. So that's what's going in my calculator. So I'm going to press second vars to get to normal CDF, which is number 2. My lower, I'm going to say negative, just a bunch of 9s. You could do negative 10,000. It doesn't have to be 9s or anything. You could do negative 1,000,000, just a very small number. My upper boundary of my shaded region is the right-hand side of my shaded region. That's 29,000. So 29,000, comma, mu is 30,000, so 30,000, and sigma is 2,000, 2,000. And I get 0.3085. Okay? So that's basically the probability of my tire life being less than 29,000 is 0.3085. Or if we wanted to say percent, because that's what the question actually said, was what percentage of the tires would have a life of less than 29,000 miles, that would be 30.85%. All right, let me show you the next one. The speeds of cars on the highway have a mean of 75 miles per hour with a standard deviation of 5 miles per hour. What would you enter into the calculator, and what percentage of the speeds of cars on the highway would be greater than 80 miles per hour? Okay, so let's look at what that looks like in terms of on the picture. I'm going to start sketching my distribution here just so I have an idea of what it looks like. If you haven't yet, you might want to go ahead and pause the video and do that yourself and go ahead and try to find the answer. So this would be a good time to pause. Okay, so we're looking for the percent of cars that have a speed greater than 80. Now, interestingly enough, on this particular problem, 80 is exactly 1 standard deviation higher than 75, so I could use the empirical rule. And according to the empirical rule, let me see if I have a pencil, this would be 13.5%, this would be 2.35%, and this would be 0.15%, and altogether that would be about 16%. Now, I'll tell you right now, it's not going to be exactly the same because the calculator is going to be more precise than the empirical rule. The empirical rule is just it's sort of a broad picture of how it works and an approximation for each of those percents. So it's going to be close to 16%, but it's not going to be exactly that. So we're being asked for a percentage of speeds of cars greater than this. Okay, so let's think about our boundaries. My lower bound, because it's on the left, is 80. My upper boundary is positive infinity, but I'm just going to say like 999. All right. You could say whatever super large number you want. My mean is 75, and my standard deviation is 5. So that's what's going in my calculator. So let me hit second, vars, hit the number 2, and I'll put 80 in for lower. And if your calculator just asks for these things, you just arrow down and put them in. Comma, 999. Let's make it 9,999. Why not? Comma, 75, comma, 5. And we get 15.8%, 0.1586. So as a percentage, what percentage of the speeds of cars would I expect to be bigger than 80 miles an hour? That's going to be 0.15, sorry, yeah, that's the probability, or 15.86%. Now that's very close to 16%. So you can see that the empirical rule is not very far off. The empirical rule is just kind of rounded to make it easy to deal with. One more thing to point out here. I may have lost my train of thought of what I wanted to point out. I did indeed. Oh, remember that the reason you don't have to, we're doing something to the right of, we don't have to subtract here. We're not going to do any subtraction from 1 when we're using the calculator, because the whole point of subtraction from 1 was that the Z-score chart, which I have misplaced. Let's see, I thought I had it handy. Here we go. This guy specifically shows us numbers that are less than, which means to the left of. Okay, so the table only tells us less than. So if we want something like greater than or between on the table, we have to manipulate this. Maybe subtract from 1 or subtract 2 of them from each other. But the calculator specifically asks me, you want it to be between what and what? And by asking me between what and what, it's narrowed down to exactly what I need. I'm not going to have to subtract from 1 or do anything else to manipulate it. Okay, here's your last example. So I would go ahead and pause your screen, hit pause, look at the screen, keep this up, and go ahead and do this problem and see what you get. Okay, so it says a grading scale is set up for 1,000 students' test scores. The scores are normally distributed with a mean of 75 and a standard deviation of 8. So mu is 75, and sigma, standard deviation, is 8. What would you enter into the calculator, and what percentage of the scores on the test would be a B? And then they tell us what it means to be a B, between 80 and 89. All right, so let's go ahead and switch over to what that looks like on paper. Okay, so this is what I'm looking for, this little shaded region here. So I have to figure out what that means in terms of lower, upper, mu, and sigma. So this is my lower boundary. The lower is always the left. You might want to just think L, L goes with L. And my upper boundary is the right-hand side of the section I'm looking for. Here's mu, and sigma, remember, is the width of each of these sections. Well, so sigma here is 8, we were told. So those are the 4 things I need to put in. So on my calculator, I hit second, It's actually clear. And then I hit second, vars, number 2. So my lower boundary is 80. My upper boundary is 89. This time, remember, we're not going to have to do anything like 9999 or negative 9. We're not going to have to do a really big number or a really small number because it doesn't keep going forever on one side. They gave me very specific parameters, and it's closed on both sides. So just from 80 to 89, and then mu is 75, and then 8 is my standard deviation. And I type that in, and I get 0.2259. So that means if I'm talking about it as probability, the probability of someone scoring between 80 and 89 is 0.2259. If I want to ask about percent, that would mean 22.59% of those students scored a B. If we wanted to, we could also be asked how many students made a B, because we were told in the original problem, we were told that we had to have 1,000 students. So I would do 1,000 students times 0.2259, and I would find out that 225 students made a B. Also keep in mind that this is the percentage of the total area here under the curve. So out of all the area under the curve here, the percentage that falls between 80 and 89 is 22.59. I hope that has helped you, and I hope that you are ready to do all your normal distribution problems. And feel free to come back and join us on another video, and have a great day. Bye.